Welcome back. In this segment, we will introduce the two-dimensional complex exponential signal. It's the extension of the one-dimensional complex exponential. It is, of course, nothing else than a cosine for its real part and a sine for its imaginary part. Complex exponentials are probably the most important signals in signal processing. They go through LSI systems with their frequencies unchanged, and they're the building blocks of any signal, as we'll see in week 3. Their periodicity property also is responsible in determining what constitutes low and high frequencies in the normalized frequency spectrum of a digital signal. The two-dimensional cosine is also an important signal since evaluated at various frequencies, it forms the set of bases of a transformation, the discrete cosine transform, or DCT, which is widely used in image and video compression, as we will see in detail in weeks 9 and 10. The basic idea when the DCT is used for compression is that it decorrelates the data. Each of the DCT coefficients contains information that none of the other coefficients contain. Now, some of the coefficients contain a lot of information, or as we say, the energy of the signal is compacted in a few coefficients. Well, other coefficients contain very little information, and therefore they can be discarded or coarsely quantized without much loss of information. So let us look at the specific details of the complex exponential.
Complex exponentials are very important signals in digital signal processing. Here we see a two-dimensional complex exponential at frequencies omega 1, omega 2. They're important for at least two reasons. The first one is that they're eigenfunctions of linear and spatially invariant systems. Don't worry about the details, the fine details at this point, we'll talk about it later, but what this means is that if I have an LSI system, that's a system that is both linear and spatially invariant, and put at the input, at its input, a complex exponential like this one, j omega 1 n1 plus j omega 2 n2, then the same complex exponential will appear at the output of the system. So these complex exponentials simply go through these linear and spatially invariant systems, with a possible change of the amplitude that will become, let's say, A, and the possible addition of a phase shift. And the second important property is that these complex exponentials are the building blocks of any signal. As we'll see later, I can write any signal as a weighted sum of these complex exponentials. Now, another form to describe these complex exponentials is with this formula attributed to Euler. So e to the j omega 1 n1, e to the j omega 2 n2 is the polar representation of this complex signal, and this is equal to cosine of the argument plus j sine of the argument, and that's the Cartesian representation of the complex function, the real part, and the imaginary part. It should be clear, looking at either the polar or the Cartesian representation, that the magnitude of this complex exponential, each one of them actually, is equal to 1. Right? From the Cartesian is cosine squared plus sine squared, and that's equal to 1. The first question we want to address here, the first property we want to examine is the periodicity of these complex exponentials with respect to the frequency, omega 1, omega 2. As it's straightforward to see here, these complex exponentials are periodic with respect to frequency, with period 2 pi in both directions, 2 pi in the omega 1 direction, 2 pi in the omega 2 direction. So if we simply write e to the j omega 1 plus 2 pi n1 e to the j omega 2 plus 2 pi n2, then this is clearly equal to I just break it down to this one. Right? And if I look at this guy here, it's a cosine plus sine, cosine 2 pi n1. n1 is an integer, so it's a cosine of an integer multiple of 2 pi, which is equal to 1. And the sine of integer multiple of 2 pi is 0. Therefore, this is equal to 1. And so is this. And this is equal to this. All right, so this is just the proof, if you wish, that indeed the two-dimensional complex exponential is periodic with respect to frequency, with period 2 pi in both directions. This same property, actually everything I just mentioned in this slide with respect to the two-dimensional complex exponential, holds true for the one-dimensional complex exponential, or the three-dimensional, or the multi-dimensional in general complex exponential. Let us look now at the periodicity of this two-dimensional complex exponential with respect to the spatial coordinates, n1 and n2. So the question is the complex exponential always periodic with respect to n1 and n2? So if it were periodic with periods n1 and 2, then this equality should hold true. Whenever n1, if we substitute n1 plus capital N1, and whenever n2, we substitute n2 plus capital N2, then if it were periodic, this should be equal to e to the j omega 1 n1, e to the j omega 2 n2, right? So the question, in other words, is can I always find the capital N1, capital N2 so that this equality holds true? Well, let's see. If we just expand this or break it down to its components, I have this for the first exponential, e to the j omega 2 n2 times e to the j omega 2 capital N2, and this is equal to this. Now this cancels out with this, and this one cancels out with this. Therefore, what I'm left with is that this should hold true. And from this, I should have that omega 1 n1 is an integer multiple of 2 pi, and that omega 2 n2 should be an integer multiple of 2 pi with another integer here, right? So therefore, from here, capital N1 is equal to k1 2 pi over omega 1, while capital N2 should be equal to k 2 pi over omega 2. Clearly, n1 is an integer, k1 is an integer, therefore, for this equality to hold true, 2 pi over omega 1 should be a rational number. That is the ratio of two integers, p over q, right? And the same should hold true for this one, so this should also be a rational number, p over q, right? So this is what the analysis tells us, right? As long as 2 pi over omega 1 and 2 pi over omega 2 are rational numbers, then I can always find a capital N1 and a capital N2 so that the two-dimensional complex exponential is periodic with respect to N1 and 2, right? So that's what we should keep in mind. So just for a one-dimensional, or let's say a two-dimensional thing, if I have e to the j 3 n1 times e to the j 4 n2, then here is omega 1 is, right, from here omega 1 equals 3, omega 2 equals 4, and therefore 2 pi over omega 1 equals 2 pi over 3, therefore, which is not a rational number. And the same is true for 2 pi over omega 2. Therefore, this two-dimensional complex exponential is not periodic with respect to n1 and 2. And this analysis here again holds true for one-dimensional discrete complex exponential signals, three-dimensional, four-dimensional, multi-dimensional complex exponentials in general. So, in summary, what we have seen in the last two slides is that unlike the continuous time complex exponential, which are always periodic in the time or spatial domain, and they're not periodic in the frequency domain, the discrete time complex exponentials are periodic in the frequency domain and may or may not be periodic in the spatial or time domain, as we just saw right here. To illustrate the previous two properties of the discrete cosine, we show here a one-dimensional cosine function, cosine omega n, for various values of the frequency omega. Now, omega in all cases involves pi, therefore this cosine is periodic in the time domain. Time is the horizontal axis, or discrete time n, right? So for example, here for omega equals pi over 8, the period is 2 pi over omega, which is equal to 16. The period here is equal to 8, equal to 4, equal to 2, and so on. So the period keeps decreasing as you move to the right, therefore the frequency keeps increasing. So for omega equals 0, cosine of 0 is equal to 1. This is the signal that does not have any other frequency other than the 0th frequency, the DC signal. Omega equals pi over 8. We see that the frequency increases. We see, right, from here to here is one period of the signal. Pi over 4 keeps increasing, and at omega equals pi, this is the highest possible frequency of the discrete cosine. And as a matter of fact, cosine pi n equals to minus 1 to the n. So the values of the signal keep alternating. It switches from 1 to minus 1 and back to 1 and so on. So this is the highest possible variation of the signal. Now, as the frequency keeps increasing from omega equals pi to 2 pi, right, we see that the frequency of the variation of the cosine keeps decreasing. As a matter of fact, this and this signal is identical because 3 pi over 2 plus pi over 2 equals 2 pi. So these are two complementary angles, and cosine of pi over 2 equals cosine of 2 pi minus pi over 2, which equals 3 pi over 2, right? So in general, I have cosine A equals cosine of 2 pi minus A, right? And similarly, these two are the same signals, and these two are the same signals. So this particular discrete cosine is periodic in the time domain because we chose the frequency omega carefully. And then the other property is that this discrete cosine is periodic in the frequency domain with frequency periodic with period 2 pi. And therefore, the range of frequencies that this cosine can change are from 0 to pi. 0 is the lowest frequency, pi is the highest frequency. I move to 2 pi, keep decreasing the frequency, and then omega equals 2 pi, cosine of 2 pi is also equal to 1. This is a constant signal, equals the cosine at 0 again. I've completed a full period that way in the frequency domain. Similarly to the previous slide, we show here the values of the two-dimensional cosine omega 1 and 1 plus omega 2 and 2 for various values of the frequencies omega 1 and omega 2. So we consider the frequencies 0, pi over 8, pi over 4, pi over 2, and pi. And since pi is involved, the resulting cosine is periodic in the spatial domain. Instead of showing it as a 3D plot, we show this cosine as a two-dimensional grayscale image, where white corresponds to the value 1, black to the value -1, and gray to the value 0. The axes have this orientation shown here, and each of these blocks is an 8 by 8 block. Okay, so if we look at this image, for example, then this shows cosine 0 and 1 plus 0 and 2, so cosine 0 is 1, so this is a constant image with a value of 1. If we look at the first row here of images, then they all have omega 1, 0, so therefore they show cosine omega 2 and 2 for various values of omega 2. If I look, for example, at this image here, then this is an image of cosine pi over 2 and 2, right? For this particular one, the period is 2 pi over 2 equals to 4 pixels or 4 samples, right? So if I take one line of this image and see how it looks, then we see that there's a value 1, followed by value of 0, followed by the value of -1, followed by the value of 0. So this is one period of the cosine pi over 2 and 2. And since this cosine is independent of the value of n1, it means that for all n1s, the same value of this cosine will be true. Therefore, you see these vertical stripes, right? It's the 1 pixel wide, so all these values, for example, here are equal to 1. And if I look also at this cosine, this represents cosine pi n2, which as we saw is equal to -1 to the n2. So this is the highest cosine in the n2 direction. I have 1 and -1 alternate. And if I finally look at this cosine here, this is cosine pi n1 plus pi n2, and you can easily verify that this is equal to -1 to the n1, -1 to the n2. So clearly the pixels alternate between -1 and 1, and this is the highest two-dimensional cosine that we can have. We are going to encounter these images later on in the course when we talk about compression. This will be the basis function signals of the discrete cosine transform, which we will use to decorrelate data in JPEG as well as in video compression.